Welcome to my full AQA A-Level Physics Paper 2 lesson. We will be covering all content all the way from sections 3.6.1 to 3.8.1.8, which is the end of everything covered on Physics Paper 2. So to begin, we're going to begin with thermal physics. So we begin on section 1, which is the thermal energy transfer. Let's begin with the internal energy. Internal energy, or U, is the sum of the randomly distributed kinetic and potential energies of all particles in the system. Our first law of thermodynamics is delta U equals Q minus W, or the change in internal energy is equal to the heat added to the system minus the work done by the system. So the heating and work, so we've got when a system is heated, its internal energy increases, leading to an increase in temperature or a change of state. Work done on a system is also going to increase its energy, which will increase its internal energy, such as compressing a gas, where work is done to the system. We also have specific heat capacity, or C. The specific heat capacity of a substance is the amount of heat required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius, or 1 Kelvin, as change in temperature is equal to, they are equivalent if you have change in Kelvin and change in degrees Celsius. The formula for specific heat capacity is Q equals mc delta theta, where Q is equal to the heat energy transferred, m is equal to the mass of the substance, and C is equal to the specific heat capacity, and delta theta is equal to the temperature change. So that's the heat energy transferred is equal to the mass of the substance multiplied by the specific heat capacity multiplied by the temperature change. Now, as I will repeat, the temperature change in Kelvin is equal to the temperature change in degrees Celsius. So now we've got continuous flow. So we have latent heat, and latent heat of a substance is the heat required to change the state of a kilogram of a substance without any change in temperature. Now it's important we note that there's no change in temperature. The specific latent heat of fusion is when we go from a solid to a liquid or a liquid to a solid. And the specific latent heat of vaporization is also known as going from a liquid to a gas or a gas to a liquid. So the formula for specific latent heat is Q equals mL, where L is the specific latent heat, Q is the energy transferred, and M is the mass of the substance. So practical experiments involved with thermal physics is the electrical method. So we use an electrical heater to determine the specific heat capacity by measuring the heat supplied and the resulting temperature change. We also have a method of mixtures where we mix different substances of different temperatures and we measure the equilibrium temperature to calculate specific heat capacities. We've then got ideal gases. We have a first gas law, which is Boyle's law, which is at a constant temperature, the pressure and volume of a gas are inversely proportional. In other words, PV equals a constant. We now have Charles's law, which is at a constant pressure, the volume of a gas is directly proportional to its absolute temperature, or V over T is a constant. We then have pressure law, which is at a constant volume, the pressure of a gas is directly proportional to its absolute temperature, or P over T is constant. We also have the ideal gas equation, which combines all of the three gas laws, which is PV equals nRT, or PV equals lowercase n, uppercase r, uppercase t, where n is the number of moles, r is the universal gas constant, which is 8.31 joules per mole Kelvin. We also have T, which is temperature in Kelvin. So that essentially means that pressure times the volume is equal to the number of moles multiplied by the universal gas constant multiplied by the temperature in Kelvin. Now to convert between degrees Celsius and Kelvin, we just add 273.15. Or do the opposite to get to degrees Celsius. We then have work done by the gas. Work done by gas during expansion or compression at constant pressure. We have W equals P delta V, where pressure is equal to P and delta V is equal to change in volume. That means that the work done is equal to the pressure multiplied by the change in volume. We have practical experiments. For this, we have Boyle's law, which we use a syringe and a pressure sensor to measure pressure and volume. We also have Charles's law, which is measuring the volume of a gas at different temperatures using a water bath and a gas syringe. We also have molecular kinetic theory model, which explains macroscopic properties of gases in terms of microscopic behavior. We then have something called Brownian motion, which is observed movement of particles in a fluid or gas, which is evidence of the existence of atoms and molecules. We have this in things like smoke, for example, which is basically the random movement of particles, which is evidence for the existence of atoms and molecules. We also have kinetic theory equation, which relates pressure, volume, temperature for an ideal gas to the kinetic energy of its molecules, where PV is equal to the kinetic energy, which is equal to a third mc squared, where or CRMS squared, where CRMS is the root mean squared speed. The N is capital N, which is the number of moles, and the M is the mass of one molecule. So that means that the pressure times the volume is equal to a third multiplied by the number of moles multiplied by the mass of one molecule. Sorry, the number of molecules multiplied by the mass of one of these molecules multiplied by the root mean squared speed squared. We then have our average kinetic energy, which is for an ideal gas, the average kinetic energy of a molecule is proportional to the absolute temperature. This means that a half m CRMS squared is equal to 3/2 kT, where K is our Boltzmann constant and T is our temperature, yet again in Kelvin. This brings us on to 3.7, which is fields and the consequences. We have 3.7.1, which is fields. So we've got concept of force fields. We've got a force field as a region wherein a body experiences a force due to the presence of another body. We have the gravitational fields, which are caused by mass, and they're always going to be attractive. We have electric fields, which are caused by charges. They can be attractive or repulsive. And we've also got one last one, which is magnetic fields. It's caused by moving charges or magnetic materials. We then have 3.2.3, which is gravitational fields. So we've got Newton's law of gravitation, which is the force between two masses or 2 point masses is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. This gives us the equation F equals gmm over r squared, where one of the m's is the mass of one of the point masses and the other m is equal to the other point mass. We have g, or capital G, in that equation as well, which is equal to 6.67 times 10 to the minus 11. So that's F equals gmm over r squared, where r is additionally the distance between the 2 point masses. We also have the gravitational field strength, which is defined as the force per unit mass experienced by a small test mass in the field, where this gravitational field strength, or G, is equal to the force experienced divided by the mass. For a radial field, however, we have G equals gm over r squared, where the m is the mass of the mass of the planet or object that we are in the field of. We then have gravitational potential, which is the work done per unit mass to move a small object from infinity to a point in a field. This is given to us via the formula V equals minus gm over r. It's a minus because as we do work against the field, we approach a overall V value, or our gravitational potential, of 0. And orbits of planets and satellites is our next part, which is involving circular orbits to start with, where we have our centripetal force, which is provided by gravity. It keeps planets and satellites in orbit. We also have Kepler's laws, which are that planets move in elliptical orbits with the sun at one focus. We then have the fact that lines joining a planet to the sun sweeps out equal areas in equal time. So we also have the third law, which is the square of the orbital period is proportional to the cube of the semi-major axis of the orbit, also known as t cubed, is directly proportional to r cubed. So t squared is proportional to r cubed. So we have our energy considerations, where we have the total energy of an orbiting satellite is the sum of its kinetic and potential energy, as we know from internal energy. We also have our escape velocity, which is the minimum velocity required for an object to escape from the gravitational field of a planet, which is given to us by VE equals 2gm/r. We also have electric fields, which is 3.7.3, where we have Coulomb's law. So we've got the force between 2-point charges is directly proportional to the product of their charges and inversely proportional to the square of the distance between them, given to us via the formula F equals KE Q1 Q2 over R squared. We also have 1 over 4 pi epsilon naught, where epsilon naught is approximately around 8.85 times 10 to the minus 12. So that's what K is equal to. So that gives the formula F equals 1 over 4 pi epsilon naught multiplied by both their charges, multiplied by each other over R squared, which is the distance between the charges squared, which is F equals K QQ over R squared. We have electric field strength, which is defined as the force per unit charge experienced by a small positive test charge in the field, which is given by E equals F over Q. Electric potential is the work done per unit charge to move a small positive charge from infinity to a point in that field. It's given to us by V equals KQ over R. Or, as we know what K is, it's 1 over 4 pi epsilon naught multiplied by Q over R. That's the electric potential, given to us also by the letter capital V. We then have electric potential difference, which is the work done to move a unit charge between 2 points in a field. This is given to us by the equation delta V is equal to V2 minus V1, which is basically just the change in energy, or the change in electric potential difference, measured in joules, of course. We then have capacitance, which is 3.7.4. We have definition of capacitance, which is essentially the ability of a system to store charge per unit voltage. And we know this because of our equation C equals QV, or as most people like to pronounce it, Q equals CV. We have now parallel plate capacitors. In a parallel plate capacitor, we have our capacitance of a parallel plate given to us by C equals epsilon naught A over D, where epsilon naught is the permittivity of free space, which is, as I previously said, it's 8.85 times 10 to the minus 12. A is our area of the plates, and D is our separation between the plates, giving us our formula that I just said, C equals epsilon naught A over D. This brings us on to energy stored in a capacitor, where we have a few equations for this, which is the energy stored in a capacitor is given by E equals a half QV, which is also equal to a half CV squared, which is also equal to a half multiplied by Q squared over C. Now we can derive all of these via our equation that I just listed a minute ago, which is Q equals CV. But we are actually given all of these equations in the formula book. We have our next section, which is charging and discharging capacitors. We have a time constant, which gives us the time required for a charge of voltage to decrease by 1 over E, or approximately 37% of its original value during discharge. The time constant is equal to RC, which is the resistance of the fixed capacitor multiplied by the capacitance of the capacitor. We then have our exponential decay of charge, which is given to us by the equation Q equals Q naught e to the minus t over RC. We have our exponential growth during charging, however, which is Q equals Q naught multiplied by a total of 1 minus e to the minus t over RC. That's the exponential growth during charging, where Q is charge. 3.7.5 magnetic fields. So magnetic flux density, B, is the strength of the magnetic field. It's measured in Teslas. It's usually quite a small number, but sometimes we have unrealistically large numbers. Force on a current carrying conductor, which is given to us via the equation F equals BIL, or F equals BIL sine theta. But we're just going to use BIL for this exam. We have Fleming's left-hand rule for this, which determines the direction of force in a current carrying conductor in a magnetic field. The left-hand rule is where we point our thumb, our index finger, and our middle finger all perpendicular to each other, where our thumb is the force our index finger is the field, and our middle finger is the current. I like to say it as force field current. We have moving charges, or force on moving charges, sorry, which is the force on a charged particle moving through a magnetic field, which is given to us by F equals BQV. We also have a sine theta on the end of it, but we don't need to worry about that. It's just F equals BQV, as sine theta just goes to 1, usually. We have magnetic flux, which is the product of magnetic flux density and the area through which the field lines pass, which is given to us by phi equals BA cos theta, where phi is our magnetic flux. So Faraday's law of magnetic induction is the induced EMF in a coil is equal to the rate of change of magnetic flux linkage, which is given to us via the equation epsilon equals minus d n phi over dt. But that's not used very much, really. We've got Lenz's law, which is the direction of induced EMF is such that it opposes the change in magnetic flux that produced it. We've then got the alternating current, AC, and transformers. We have AC, which is sinusoidal voltages and currents, characterized by the root mean squared RMS values, which is IRMS equals I0 divided by root 2. We have the same for our voltage RMS, which is VRMS equals V0 over root 2. Our transformers, a transformer equation is Vs over Vp, where Vs is the voltage across the secondary coil, and Vp is the voltage across the primary coil, which is equal to Ns over Np, which Ns is the number of coils in the secondary coil divided by Np, which is the number of coils in the primary coil. We then have our efficiency, which is given to us via P output over P input. You can work out that as a percentage by multiplying it by 100, of course. P is power. We then have 3.8, which is nuclear physics. We've got radioactivity. 3.8.1, which is alpha particles scattered by a thin gold foil, leading to the discovery of the nucleus. Types of radiation, we've got alpha, which is helium nuclei, highly ionizing and low penetrating. Beta, which is electrons and positrons, moderate ionizing power and penetration, sort of in between. And then you've got gamma, which is high energy photons, low ionizing power, high penetration. We've then got radioactive decay, where we've got a decay law, which is n equals n0 e to the minus lambda t, where lambda is a decay constant. N0 is our number of nuclei to begin with, and n is our number of nuclei to calculate at that point in time, depending on t value, where t is time. Activity A is equal to the decay constant multiplied by n. Half-life, or t to the half, is given to us by ln 2 over decay constant. We then have nuclear instability, where the binding energy is required to separate a nucleus into its components, protons and neutrons. The mass defect, of course, is the difference between the mass of the nucleus and the sum of its constituent nucleons, given to us by the equation E equals mc squared. The nuclear radius is given to us via the formula using the closest approach of half particles and electron diffraction, which is R equals R0 a to the third, where R0 is usually just given to us, which is around 1.2 femtometers usually, multiplied by a to the third, where a is the nucleon number and r is the radius to calculate. Now, it's important to note that this is just an estimate, and it's actually going to be an overestimate because when we have alpha particles going towards a nucleus, they're not actually going to hit it directly because they're going to stop just before they hit it. So it's usually an overestimate. But to get around this, we use electron diffraction, and we can use electron diffraction also to find out the nuclear radius. And we do that by shooting a beam of electrons at a nucleus, and we get a diffraction pattern that looks similar to the it looks exactly the same to the single slit diffraction back from paper 1. We don't need to know how we find out the radius from this method, but we just need to know it's there. We've then got our mass energy equivalence, which is equals mc squared. Binding energy per nucleon gives us an indication of the stability of a nucleus. Induced fission, which is fission of heavy nuclei, or uranium-235, by thermal neutrons, leading to a chain reaction. We then have nuclear reactor components, which we have the moderator, which slows down neutrons, control rods, which absorb excess neutrons, and coolant, which transfers heat from the reactor. So the purpose of the moderator is basically just to slow down the neutrons. So this is so that the neutrons can essentially get to a thermal temperature, so we can increase our chance of fission occurring. And this type of fission that we call it is actually induced fission. Our control rods, which absorb excess neutrons. I don't really like the definition, to be honest, because it doesn't absorb excess neutrons as such. It's there to control the rate of fission. So, for example, in an emergency, we can have an emergency shutdown, and we can do this by inserting the control rods. And what this will do is it will absorb all of the neutrons that is in the core. So they'll go in between the fuel rods, and they'll absorb all the neutrons, and will stop the fission occurring. Which means that we can control the rate of power output, which makes nuclear power plants quite good in terms of like when we have power surges and things like that. And when we do need to shut off power for any reason, it's quite easy to do with the control rods. Control rods are usually made out of things like boron and cadmium, I believe. Coolant. For our coolant, we usually just use water, or I think we can use carbon dioxide as well, but water is the cheapest option, and it does the job just fine. Moderator, I think we can use water for the moderator as well. It slows down the neutrons, but for the moderator, actually I'm not sure if we do use water, but the thing that's important to note for the moderator material is that we want something with a very small nucleon number, and the reason for this is that we'll basically slow down neutrons faster with a lower nucleon number. Got safety aspects, which is the handling and storing of the radioactive materials. So shielding, remote shielding, and emergency shutdown procedures. I just went through the emergency shutdown procedures with the control rods, so we'll insert them fully, which will stop fission from occurring. We then got remote handling, which is essentially, well, people don't really need to be near nuclear power plants if they can just control it remotely. So you're not exactly going to be sitting in the nuclear core to control it. Instead, you can just access it via computer, some distance away. So you're a bit more safe. You've then got the handling of your fuel rods. So when our fuel rods are used, finished with, they're called spent fuel rods, so they need to be replaced with new fuel rods. But it's important to note that our spent fuel rods are highly radioactive compared to new fuel rods, and this is because of our radioactive byproducts all over it and stuff. It's going to be emitting a lot of radiation compared to the new ones. So first of all, what we do is, because it's still going to be emitting loads of heat, we place them in a water bath or a coolant bath, or usually in the facility where we have our nuclear plant, and it's held there for quite some time, maybe a few years. But obviously they can't sit there forever. So what they do after that is they will transport them off to a plant, which they will be melted down with chemicals, and all of the products like excess uranium that maybe hasn't finished decaying yet, they'll reuse it. Excess radioactive material, they might be able to farm some of it off to reuse some of it. But all the rest, what they do is they undergo something called vitrification, which is where they basically put it in a non-porous glass so that it doesn't leak. So it's called vitrification. They vitrify it, which is where they put it inside of a glass, and this makes it so that it doesn't leak everywhere because glass is non-porous. And what they then do is they put this vitrified radioactive material, which is non-porous and won't leak, and they put it in safe storage in a place probably underground, depending on the half life of this material. If it's got a very large half life, they might want to bury it underground because it's going to be there for a long time. But then if it's got a short half life, they might not bury it so far underground. Say if it's got a very small half life and it might stop being radioactive in a few years' time, they might just put it in some concrete shielding somewhere, away from people, of course, or as far away from people as you can, and then they'll be able to extract the material once it's stopped being as radioactive. So yeah, that should be most of the safety aspects covered. I think most of the other safety aspects are just common sense, to be honest. Knowing your basic sort of safety stuff with nuclear stuff and transformers, electricity, all that kind of thing. It's just common sense stuff, really. I hope you enjoyed this lesson. Should be covering all of AQA Physics Paper 2 for the A-level specification. I hope we've covered all of the key concepts, equations, and practical applications necessary for understanding these topics. Right, thank you very much. See you soon.